Second step in the process is the evaluation of vapor intrusion risk using soil gas data. In response to public comment, the final draft supplemental vapor intrusion guidance was revised, 1, to clarify recommendations regarding soil gas sampling depths for existing and future buildings, 2, to clarify recommendations regarding how the capping effect impacts soil gas sampling design, 3, to add an attachment describing lines of evidence and their use, and 4, to explain the limitation of passive samples. Step 2 describes a general strategy to integrate vapor intrusion screening into overall soil gas contamination investigations. Collecting and analyzing soil gas concentration data as a primary line of evidence for vapor intrusion is an appropriate early screening step to evaluate the potential for vapor intrusion. Soil gas concentration data is generally preferred as a line of evidence for assessing vapor intrusion risk over groundwater or soil matrix concentration data for several reasons, including soil gas is most closely associated with emissions from subsurface contaminated media, uncertainty in predicting contaminant partitioning from groundwater or soil moisture to soil gas due to uncertainty in organic content in soil, moisture content, and Henry's law constants, uncertainty in predicting transport through the capillary fringe, heterogeneity in the soil matrix. Soil matrix sampling is subject to loss of volatiles, and the standard reporting limits for vapor-forming chemicals in soil, 5 micrograms per kilogram, are typically greater than estimated levels of concern for some vapor-forming chemicals. Soil matrix samples can be qualitative indicators of a release area, but are not acceptable for calculating vapor intrusion risk. For Step 2A, the distribution of shallow soil gas contamination should be evaluated. The objective is to evaluate the nature, distribution, and extent of shallow soil gas contamination, both laterally and vertically, and use that information to evaluate vapor intrusion risk to building occupants. For evaluating the lateral distribution of shallow soil gas contamination, soil gas sample locations should be selected to help identify release areas and the distribution of contamination. Soil gas sampling locations should initially be based on the location of known or suspected releases and laterally step out following a grid or radial sampling pattern. Samples should be spaced to provide a good understanding of the location of all release areas and a conceptual understanding of how soil gas contamination can be transported from those areas to current and likely future buildings. Specific locations selected for soil gas sampling to assess each building should include areas between the building and the nearest vapor source and laterally as close as possible to the target building. Sampling should continue until the extent and distribution of contamination is reasonably understood. For evaluating the vertical distribution of shallow soil gas contamination, soil gas samples should be collected from multiple depths to generate a depth profile and provide a reasonable understanding of the vertical soil gas distribution to help identify the greatest shallow soil gas concentrations. Soil gas samples should be collected from at least 2 depths, targeting depths of known or suspected shallow contamination and providing good coverage of the recommended sampling range. In general, soil gas samples should be collected from 2 depths within the recommended sampling range of 5 to 25 feet below ground surface. In the example presented here, a sample is collected at a depth just above a known shallow groundwater plume, and a second sample is collected in the middle of the vadose zone near suspected soil contamination. For soil gas samples collected to evaluate vapor intrusion risk to building occupants, the sample depths should consider the slab capping effect, which is a result of a concrete slab acting as a barrier or cap limiting the downward flow of ambient air and the upward venting of contaminated soil gas. Specifically, less attenuation is expected beneath buildings with a slab due to the slab capping effect. Therefore, for buildings with slab-on-grade or basement foundations, vapor-forming chemical concentrations collected from exterior soil gas samples located at deeper depths are less likely to underestimate sub-slab soil gas concentrations compared to shallower exterior soil gas samples. Figures on this slide conceptual model scenarios for the vapor intrusion pathway considering the slab capping effect. Contaminant plume migration and seasonal factors, such as weather conditions, groundwater levels, soil temperature, and soil moisture, can cause significant temporal variability in soil gas concentrations. When risk calculated from a single sampling event is below the points of departure, at least one additional sampling event is recommended before concluding that subsurface contamination is unlikely to pose a health risk. Additional sampling reduces the potential for underestimating vapor intrusion risk caused by temporal variability. Sampling events should occur in different seasons as determined by average seasonal temperatures, precipitation, or fluctuations in depth to groundwater. Additional sampling events may not be warranted if vapor-forming chemicals are not detected in any environmental media within 100 feet and other lines of evidence agree that vapor intrusion is unlikely, such as the soil gas plume being stable. This slide shows a flowchart of the process for screening buildings using soil gas data. The process starts with the collection of soil gas data and the evaluation of those data to estimate the risk and hazard using the maximum soil gas concentration and an attenuation factor of 0.03. If the estimated risk exceeds the point of departure of 1 × 10 to the -6, or the estimated hazard index exceeds the point of departure of 1, proceed to an indoor air investigation at current buildings. If after the first round of soil gas sampling, estimated risk does not exceed the points of departure, then a second round of sampling should be conducted to evaluate temporal variability. If vapor-forming chemicals were not detected in any environmental media, or if after the additional sampling events, risk and hazard are confirmed to be below the points of departure, and lines of evidence are generally consistent, the building is considered low priority for further vapor intrusion evaluation. Note that an alternative attenuation factor can be used if supported by adequate technical lines of evidence. In early 2019, DTSC compiled and analyzed subsurface and indoor air data from sites in California contaminated with chlorinated vapor-forming chemicals to improve its knowledge and understanding of vapor intrusion. The study collected data from 52 sites located in 16 of California's 58 counties. These data consisted of 4,972 paired subsurface and indoor air measurements taken from 262 buildings. The data set was filtered for contaminant source strength, removing paired measurements with subsurface concentrations less than 50 times background concentrations. The data set is limited to only non-petroleum contaminants, excludes post-remediation data, and contained no data from buildings with basements. The vapor intrusion attenuation factor study is subject to several limitations. The data set is comprised primarily of data from commercial sites. Only 42 measured pairs of residential subslab data remained in the dataset after source strength filtering. Similarly, residential soil gas data was heavily impacted by source strength filtering, and 76% of the remaining residential soil gas paired measurements come from one site. These limitations make any statewide inference of residential subslab or soil gas attenuation challenging. The non-residential buildings in the dataset include a wide spectrum of building types, from very small retail businesses with minimum air exchange to very large industrial warehouses with high air exchange. Attenuation factors for different types of non-residential buildings were not evaluated. The dataset lacks information concerning the operation of the HVAC systems during indoor air testing for most buildings or the presence of preferential vapor migration pathways. Hence, the influence of HVAC operation and preferential pathways is unknown. The dataset has a large proportion of buildings with multiple data pairs, and the statistical independence of those data pairs is unknown. Data that are not independent could bias the statistical analysis. The DTSC Attenuation Factor Study database is comprised of subsurface and indoor air data collected primarily from commercial sites in California prior to 2020. The DTSC Attenuation Factor Study database is subject to several limitations such as a reliance on data from commercial sites and a lack of data sufficient to account for the factors that influence the variability in vapor-forming chemical concentrations. Therefore, the DTSC Attenuation Factor Study Database does not provide a sufficient basis for policy decisions to establish vapor intrusion attenuation factors. The Supplemental Vapor Intrusion Guidance calls for the collection of additional vapor-forming chemical concentration data in various media, along with relevant building-specific data under better controlled conditions. This information will be added to the GeoTracker database, where it can be used to reevaluate attenuation factor assumptions to build a stronger and more accurate assessment tool.